So I wanted to kind of sketch a proof of that. Right, so the idea was that we observed that if we had a proper holomorphic map F between two Riemann surfaces, x and y, which are connected, and this was important, Riemann surfaces, and this was proper and holomorphic, then by sort of removing the branch points of x and a few other points, we were able to actually turn this into a covering map, and then from that covering map we had some essentially combinatorial information that determined the covering map. So just to remind you what we got out of this, right, we got some information. So first we got this integer invariant d, which corresponded to the degree of this map. The second thing we got was a discrete set delta, which inside of y. Right, so this corresponded to the image of the branch points under F. And then the final thing we got was this transitive permutation representation. So this transitive representation rho that took the fundamental group of the base minus the image of the branch points into the symmetric group on D elements. And the idea of this, to remark, the fact that it's transitive has to do with the fact that x is connected. So one way of understanding this representation is, for example, fix a point in y away from this set delta and look at the pre-image. So that consists of d points. And if you look at the image downstairs at that point, if you take a loop in y minus delta, then you can look at the lifts of that loop upstairs into x. And obviously there's a choice for each. I mean, the only choice you're allowed to make is where the starting point is. So that's somewhere in the fiber over the point, and exactly where this element in the symmetric group is exactly when you trace out the loop where you end up. And the idea that it's transitive has to do with the fact that, for example, one way to see that it's transitive is related to the fact that it's connected is just to take 2 points in the fiber, connect them by some path upstairs away from the preimage of delta, and then see that downstairs that gives you a closed loop. So that would be an element whose image under rho took the given point to the other point. We'll see. We'll come back. I just wanted to emphasize that because it'll come up in the proof. Okay, so this was sort of the monodromy. This had to do with somehow the monodromy of F. And the point of the existence theorem was that actually, given this information, one could, so in other words, an integer, a Riemann surface Y with a discrete subset, connected Riemann surface Y with a discrete subset, and some kind of transitive representation of this sort, one could cook up a new Riemann surface X and a holomorphic map F so that its monodromy was the given information. So maybe I'll just write that down. So as I said, this was a way of finding interesting examples of Riemann surfaces sort of from kind of topological or combinatorial information. Okay, so then the Riemann existence theorem just said given the combinatorial data, there exists a Riemann surface X, holomorphic map. Okay, so the proof of this, I'll just give a sketch of it. Maybe leave the details to you. So the main idea is, the first thing is just given this combinatorial data, it follows from kind of standard topology, which of course one should do if one's doing it for the first time, but that there's a map, a covering map, F0. This is a covering map that takes some set, what did I call it? X0 to Y delta with the given data. Okay, so that's just this is just a topological thing. It's very similar. I mean, it's obviously a little more involved, but it's very similar to the idea of constructing like a universal cover. It's the same basic construction. And of course, the point is this is a Riemann surface, and we can set up this construction. So this map is say a smooth map that's actually a local diffeomorphism at each point of x0. So this guy gets a smooth. I mean, basically, you can set everything up so this is a biholomorphism, and not a holomorphic map. So you can induce a Riemann surface structure. So in doing so, you actually get x naught as a Riemann surface, and F0 as a holomorphic map. Okay, so the whole point is of at least this sort of from the point of view of Riemann surface theory is to extend F to some bigger space, some bigger Riemann surface X, so that you kind of fill in the holes that you've removed here. Okay, so how do you do that? So we want to okay, so let's give again an idea. So let's pick a point y1 inside of delta and choose a disk d1 about, well, such that this is such that d1 intersect delta is just the single point y1. Okay, so it's just a small disk around delta. Okay, so now, right, if we just think about it downstairs, here's sort of y, possibly with some genus, and here's the point y1 we removed. So we pick our d1, and if we look at d1 minus the point y1, right, this should be the same as say d star, and so in particular the pi 1 of d1 minus y1 is z, right? So it's generated by, once we fix orientations, which we just go around like that, and that's the generator. That's the loop that you can't contract off. Okay, so now what we want to do is to try and figure out what's going on upstairs in x0 using this representation. So we let sigma be equal to rho of. So let's call this generator here gamma. Okay, so this is an element of the, say, the symmetric group on D elements. And we can look at the, we just look at the group or the subgroup, right? So the first thing we note is because this is an abelian group, the subgroup generated by sigma is also abelian. So the thing, though, we note, though, is that, right, even though this action, this representation is transitive, right, we're actually not, to mean it's transitive means there's some element in the pi 1 that gives you the transitive action. And so since we're restricting the elements we look at to this gamma, there's no reason that the element sigma has to act transitively on the D points. Okay, so you note that sigma, need not. Okay, so then, nevertheless, it's an abelian. What we can think of it as an element of SD, and since it's acting in a kind of an abelian way, what that means is it should be decomposable into cycles that are disjoint. So we can write it. This means that this implies that, in fact, everything I said, that sigma is equal to, say, C1 up to CL, where the CJs are disjoint cycles. Something like, you send the first element to the second element, and then the second element to the first element. But that times like the third element to the fourth element, and the fourth element to the third element. That would be an element that's allowed in the symmetric group of four elements. Okay, so then you should try and convince yourself that what this means in terms of the preimage of D1 minus the point under F0 is that each of these cycles corresponds to a component of that guy. So each right, so the picture should be the picture should be, let's say there's like two cycles. So here's sort of the point with the disk removed. Like, let's say we had a kind of two-sheeted cover where you went around once corresponded to going up. So this would be a kind of two cycle, a cycle with two elements. So something like C1 is equal to 1, 2, say, and then let's just suppose there could be another one that's just maybe with one element. So this would be, say, C2 equal to just 3. It doesn't move anything. And something with like the more elements is sort of the more times it winds around. And the idea is, of course, since the representation is supposed to be transitive, it means there's some other loop that kind of connects them. But we don't see it when we just focus on D1. So now, one should sort of convince oneself that, and this obviously takes a little bit of work, but we have a pretty good model of what this should look like in the terms of Riemann surfaces. So, one should convince oneself that that Zi, the mapping down to D1 minus the point by the restriction of F0 is the same as taking, right, you should convince, first of all, the first thing to convince yourself, which is kind of clear, is that this is actually topologically an annulus. And so what we want to try and do is identify it with the punctured disk, and then with the standard coordinate z, and then just consider the map z to the length of the cycle I. Right. So there's clearly, what one wants to say is that there's a sort of a chart here, which I called psi I, and a chart here, so that this whole thing commutes. So in other words, as Riemann surfaces, the behavior of F0 is entirely determined by this map. So then the final thing is one wants to then use the fact that we can just, we can extend this guy inside of the closed disk to the closed disk, and everything is well behaved, and we get exactly the kind of behavior we expect. So that's the final part of the proof, which is to essentially use a kind of gluing argument to say that we can use the map phi0 and the map, we can use, here we have, the idea here is that downstairs at y, we have this sort of, we pick a chart y, and that's sort of forced on us by the Riemann surface structure of y, but the choice of psi 0 is made so that everything works out in this manner. And what you want to convince yourself of is that, if you kind of go the other way, where you now think of the inverse as mapping this guy, which is open subset of D, to Zi, that you can sort of take a glue, think of it as a gluing, and so glue in this disk into the component Zi, and then extend the map F0 to the image under, this new point you've introduced, which is that corresponds to the origin of the disk, just send it to yi, y1, sorry. Okay, and so the point of, the tedious part, in a sense, is to check, first of all, that this gluing gives you a well-defined Riemann surface structure upstairs, and that this extension actually gives you a holomorphic map, and then you'll be done. Okay, so maybe I'll leave that to you to work out the details. Now the point is, you then do this at every point, and then in so doing, you filled in all the possible holes, and so you constructed the desired x, and you check that over every point in y there should be a d points of x counting multiplicity, and so F0 is a proper map. So the one tricky part, which is why this you need to think a little bit more about this, is if there was already a point here and you tried to do this gluing construction, what would end up happening is you'd have sort of 2 points that were arbitrarily close to any perturbation of the point. So that would not be Hausdorff. So that would not be a Riemann surface. So that's the one subtle point. You have to check that when you do this gluing, that you actually get a Hausdorff space. Okay. All right. So that's the Riemann existence theorem, and just the idea of the proof. And as I said, it's a useful way of kind of showing from kind of topological arguments that you actually get certain types of, say, meromorphic functions. And certainly allows you to see that it's one way to see that every closed surface is a Riemann surface with respect to some complex structure. Okay, so that's that's the end of that. And so now I want to kind of switch gears and turn to talking about sort of differential calculus, how to do calculations on Riemann surfaces. So a lot of this will be kind of review of what Hayo did, but maybe with more, everything will be more explicit, so maybe people who had trouble with that will get something from this. Okay, so let's switch gears, and now we're going to talk about sort of, differential calculus, or calculus. Okay, so the first thing we're going to do is just refresh our memory of some things about calculus on the surfaces. So this will be a little pedantic, but let's just for the moment fix two open subsets of R2 and a diffeomorphism. So I'm just because it's a little bit in the interest of time, what I'm going to do is just kind of define some notions on these open subsets and prove that they're well behaved under diffeomorphisms, or later they're well behaved under holomorphic diffeomorphisms. And then you should imagine that once that's true, you can just define it on a Riemann surface by checking it makes sense in charts, rather than try and abstractly defining some of the concepts. Okay, so what is the first thing I want to remark? So, right, we want to first just talk about, say, vector fields, just very briefly, right? So recall on R2, you have these standard coordinates x and y, and then they give you these standard vector fields, ddx and ddy. Which are, in a sense, linearly independent. And the way I like to think of them is to think of them as differential operators. So these guys, they act on, say, smooth functions by taking partial derivatives. Right, so you just... this guy acts on a smooth function by taking the partial derivative with respect to y. So in general, a smooth vector field, so a smooth, say, real, I won't usually put this, but vector field is just on, say, u is just is a function v, which is equal to, and sometimes I'll just write this as x and y. So this is equal to a times x plus b times y for a and b. Say C infinity functions on u. Okay, so the point about this is, of course, the space of all of these is clearly an infinite dimensional vector space where you can add two vector fields together and multiply by smooth functions, and they act in the obvious way on a smooth function. So to make sense of this sort of invariantly, we need to right, we want to define, say, the push forward of V, and we'll just define this to be, assume we didn't make a mistake, it's A of V inverse, and then that's applied to, if you just take the standard derivative of phi and apply it to dx, and then you take the derivative of phi and apply it to, well, let's call it just x. All right, this is sort of stupid, but bear with me. But the point about this is that if we're thinking about things as differential operators acting on on functions, then what one observes is that the push forward of a vector field acting on a smooth function should be, if this definition is the same, right, the same as the vector field acting on G composed with phi, all of this composed with phi inverse. So here G is a smooth function of, okay? So the point about this is that somehow this action of a vector field makes sense in independent of coordinates, and so it makes sense, should make sense on a surface. So then the the tangent bundle of a surface sigma, this allows us to talk about the tangent bundle of a surface sigma by sort of saying it's the right. So the space of all these vector fields on a U, this the span of them is maybe you could call it the tangent bundle of U, which is just identified with U cross R2. And so then what you can do is on a surface you can use the local coordinates to kind of turn this local definition into a definition of sigma, and then you get vector fields which are sections of the vector bundle T sigma. So this is the tangent bundle. So essentially, I don't want to, again, it takes a long time to think about this if you want to be very precise, but essentially, for me, a vector field is just a smooth differential operator that is smooth in the sense that in local coordinates it looks like this form and acts in the appropriate way. And the point is, if you look at a given point, you can think of the tangent space at a point. It has a different interpretation, which is a kind of equivalence class of curves through the point which agree to first order, which again makes sense. And you have to draw all these connections between the various definitions, but just to keep this as such. Okay, so once we have this notion of vector field, which kind of allows us to differentiate, say, functions in a certain way, it turns out that it's more useful to have, for the purposes of, say, integration, to have the dual notion. So that's the notion of a smooth form. So this is the sort of dual notion. Okay, so what's the smooth form? Okay, so again, the basic idea is we start with these coordinate guys. So we have these two, so to say it's a dual means it's some kind of map from vectors into vector fields, say, into smooth functions. So there's two natural, say, forms on, let's say, we'll work on U prime now. So again, these are the coordinate ones. And this is all true on dx and dy. And the idea is basically you just think of them as objects that take a vector field v, and this spits out the function a, and they take a vector field v, and they spit out b. And again, we just take the linear span of those, and that's the space of forms. So the span of these guys is the one forms. Real one forms omega of U prime. Okay? And again, we can identify this as, this identifies the space of them as, right, when we think about this, these are supposed to be sections of, of this cotangent bundle of U prime, which is, of course, supposed to be U prime cross R2. And again, to try and build this into something global, we need to make sense of how these transform under, say, change of coordinates. So, right, so what we do is we just, again, sort of define this. So, of course, there's better ways to do this, but we define the pullback of a form So in general, we write omega is equal to, say, a prime dx plus b prime dy, or again, a prime b prime smooth functions of u prime. So we just define the pullback of omega. So this has a much simpler definition, which is so a prime composed with phi. Being really pedantic here. And so then the point is one checks that this idea makes sense with respect to this definition and that definition. So in other words, if you pull back a form omega and apply it to a vector field v, that's the same as taking the form and applying it to the push forward of the vector field. Okay, and so then that's the whole idea of this having good transformation properties, which allows us to make sense of it on a surface. So the point about one forms versus vector fields is that they're right. A vector field is in a sense differentiates a function, but if we want to think about an invariant way of differentiating a function, the right way to do it is in this language of forms, which you probably have seen, but just remind you. Right. So if we set the for a given function f in, if we just define df of df to be the one form, which is given by x applied to f, dx plus y applied to f dy, then what we see is that that it's pretty clear that if you take this one form and apply it to v, then that's the same as taking v and applying it to f. And the point is, this definition makes sense because it transforms correctly. So if we look at d of phi pullback of f, which is to say the same as d of f composed with phi, then that's one computes is the same as with this definition. It's exactly chosen as phi pullback of df. So what this means is this operator d, which takes the zero forms, say, of sigma. So everything makes sense on a manifold because of this transition property. And what it means is if we take this guy, which is the set of smooth functions of sigma, then we get a map D, which goes to the one forms of sigma. Okay? And that's a well-defined map. Okay, so that's one of the nice things about forms is they allow us to take a derivative of a smooth function and get something that we can talk about. Okay, so the other nice thing about them is that we can integrate them. We can also integrate them on oriented curves. So let's just give an idea. So suppose we have a curve C, which we parameterize by a map gamma that takes the closed interval 0 to 1 with parameter t to this curve C, which is inside of, let's just have it inside of U prime for simplicity. So if we wanted to, what we're going to say is basically we define the integral over C. Right? Notice there's an orientation on C because we can just, we have a kind of direction of t. The t is increasing. So we can define the integral over C of, let's just say dx. That's just going to be, by definition, the integral from 0 to 1 of of x. I'm always confused by this stuff. dt of x of gamma of t. Right? This is just your usual definition. And what the point about this, though, which is the useful part about this, is that if you work this out, if you reparameterize gamma, so you compose with some new, map from 0, 1 to itself, then actually this value that's, say, that's a self, like a diffeomorphism, then this definition is actually gives you the same value. So it's really an integral of the curve C and not of the choice of parameterization, even though in the definition the parameterization appears. And of course, we can define it similarly for dy, where we put a y here and then extend it to forms by linearity. So I won't write down all the details of that, but right, and okay, so that's the definition of form, right? So maybe I'll just say, well, let's say you have a prime, so then the a prime is there of gamma of t, just so it doesn't look like you can use the fundamental theorem of calculus. Okay, so this, again, the point is we have to check this, but it turns out that all of this makes sense in a surface just by doing these computations in a chart and proving what we've basically argued is that everything is independent of the choice of chart. Okay, so then, given these space of one forms, the next thing you want to look at is sort of the space of two forms, which, on the one hand, kind of arise naturally, algebraically, from the space of one forms by thinking of certain bilinear forms. The other way is they arise naturally is, on the one hand, the one forms allow you to integrate curves. You might ask if you can integrate, what do you need to integrate surfaces? And it turns out the two forms are the right way to integrate over surfaces. So let's get to that. So again, a two form is just a smoothly varying antisymmetric bilinear form on the space of vector fields. Right. In other words, if you have, say, some, well, that's bad notation. Let's call it like theta is a two form, and you plug in two vector fields, x and y, then this is supposed to be equal to right. So again, this makes sense everywhere, but you can localize it to a point. But if you work things out, it's pretty easy to see that the standard sort of primitive element coming from the coordinate is to take consider the element dx wedge dy, which acts on v and w by just taking dx of v dy of w minus dx of w dy of v. Okay? And in general, these thetas, you should convince yourself just by linear algebra that theta is just going to be some constant c times dx wedge dy on, say, on this u prime. And here, this is supposed to be like a smooth function of. Okay, so then what the point about this is, as I said, this is supposed to define, one of the points of them is they allow you to integrate over surfaces. And to make sense of that, let's just notice that if we define, I mean, one can check this from the definition, but if you sort of assume sort of the phi pullback of the behaves well with respect to wedge, but let's just make this a definition. So the pullback of a one form applied to vectors v and w is just by definition going to be the well, let's be a little careful. So the pullback of c dx wedge dy is going to be equal to, by definition, c composed with phi times the Jacobian of phi dx wedge dy. This is a definition. So this is the Jacobian of phi. Right, so the point about this is that right, we can just define now the integral over u prime of theta. This one form is just by definition supposed to be the integral over u prime of the function c dx dy, just using sort of Lebesgue measure. And the idea now is that if phi is orientation preserving, so in other words, it has positive Jacobian everywhere, right, then that actually tells us that the integral over u of phi, just the standard change of variable formula of theta, is equal to the integral over u prime of theta, right? This is just by the change of variables. So again, what this means is that you can define a well-defined notion of taking the integral of a two-form on an oriented surface, because you choose an oriented chart atlas, and then you compute it in the atlas, and if you change coordinates, you get the same answer. Obviously, there's a little more subtlety because you need to chop things up, but you observe this has linearity properties, so you can sort of do it locally and piece together. Okay, so then the final just remark, which again is somehow already implicit, is we had these we had omega 1 of sigma, and then we had these two forms, omega 2 of sigma. So we want to sort of see how we can get from one forms to two forms. So on the one hand, we can generalize this notion of wedge by defining that if we have two one forms, right, we have the wedge product of them, which acts on vectors x and y by which is clearly anti-symmetric and bilinear. So that's a way of pairing one forms together to get a two form. The other operation we have is, of course, an extension of the operator d, which is that d of omega evaluated x and y is going to be, by definition, you take the vector field x and look at the evaluation omega y, and then make it anti-symmetric by doing it in the reverse order. Okay? So you should convince yourself, I mean, obviously I haven't made any reference to coordinates here, so this is completely well-defined on a Riemann, on any surface. What you should convince yourself of is that you should figure out what this really means when you work in coordinate vector fields for a given one form. And it's pretty easy there, because then, well, maybe x and y is misleading. Let's call this v and w. But what one should convince oneself is from this fact, right? From this fact, we see that if you have take d of a function, then in fact you get 0. So this is I mean, you all know this, but just reminding everything. So the point is, we now have this operator. We have these 0 forms, which are just the smooth functions. Then we have this map D to the 1 forms, which is defined 4. And then we have this other map D, which is the right. So we call the image of this guy, the image is the exact forms, and the kernel, so the elements getting sent to 0, which what we just observed is that the image is inside of the kernel are the closed forms. And so one of the things we're going to study next time is what exactly measures the discrepancy between the two sets. So this is known as the de Rham cohomology group, the first de Rham cohomology group. And as we'll see, for an oriented closed surface, it's essentially determined by the genus, at least up to isomorphism class. Okay, so the final remark, which is, maybe I'll leave this to you as an exercise, but the final remark is that, you might ask, when a given 1 form is actually exact. And so this gives us a necessary condition, which is that it be closed. And so one thing you should check is that actually that's a sufficient condition if you have a simply connected region. So that actually is going to follow from this. I mean, it's much easier if you do it in coordinates, but it'll just follow from Stokes' theorem. So I just want to remind you of this. So if sigma is an oriented surface with boundary, so one way of thinking about this is just put sigma inside of sigma prime, where this is a closed surface or a nice surface. This is a manifold, and this is just a region which has nice boundary. You understand that in a domain and in the plane. Then the Stokes theorem tells us that if we integrate over sigma of the boundary of sigma of a 1 form omega, which we can always do, then that's the same as the integral over all of sigma of d of omega. Or this makes sense because this is omega is a 1 form. And d omega is a 2 form. And we have to be a little careful because, of course, we know this guy is oriented, but we have to put the right orientation on this. But you should work that out for yourself if you don't. I mean, you probably all know this. Okay, so that's just calculus on a general surface. So of course we want to kind of specialize to the case of a Riemann surface. Right. Okay, so we want to specialize to the case of a Riemann surface. So the way to do that is to just, again, do everything kind of in domains in R2, but instead of working in R2, we work in C. So again, now we just think of U and U prime as subsets of C, and we make the identification as usual that the coordinate on C is Z is X plus I, Y, right? And so now, instead of thinking about real vector fields, we can think about complex valued vector fields. So we have complex vector fields. And the two basic ones are going to be Z, which is equal to 1/2 x minus iy, and Z bar, which is equal to 1/2 x plus iy. And again, these are supposed to be, I mean, you should just think of them as sort of, these are just some primitive elements which you recognize as related to as ddx, but they now have values that have complex coefficients, so that's why we can multiply by I. And the idea is you should think of these guys as acting on functions C, which are C infinity, say, with this fixed unit domain, now with complex coefficients, which again we'll write as sort of the 0. But now the idea is this is just where we've kind of complexified everything. If you want, we've just tensored with the complex numbers. But okay, so then one of the things you observe, of course, is that if you apply this z bar operator to a smooth function f, then if that's 0 if and only if the function is holomorphic. The thing, though, is that one has to, I mean, that's not going to turn out to be independent of change of coordinates if we just allowed smooth change of coordinates. So that's the next thing we want to kind of see what happens, which again is just a repeat of what Io did. Okay, so similar to these complex vector fields, we define, say, complex 1 forms. And again, the basic idea is that we have dz and dz bar, which is dx plus I dy and dx minus I dy. So these are elements of so in general, if we write an element A is equal to A prime dz plus B prime dz bar, we can wonder what happens when we pull back by omega by this diffeomorphism phi. So the point is just if we kind of expand everything out and work out everything in terms of the real case, or just do it by directly, either way, you should convince yourself that this is actually equal to A of phi of z applied to phi. Well, yeah, that's plus z bar applied to phi. This is dz bar plus b of phi z applied to phi bar dz plus z bar applied to phi bar dz bar. Okay? So one of the things we see right away is for a general phi, right, a phi just mapping between, let's say a smooth map between these domains in C, even if we start with the form that only depends on dz, we'll get, from terms like this, we'll get terms that have a dz bar, right? But the observation is these guys, this is 0 if and only if phi is holomorphic, as is this term here, right? So the idea is that if phi is holomorphic, so if phi is holomorphic, then the pullback of A of omega, well, let's say A dz, why am I changing notation here? Right, this is actually going to be A of phi z dot phi dz, where again, right, I mean, this sort of makes sense because phi is a complex valued function, plus b prime of phi z bar dot phi bar dz bar. So in other words, and I'll stop here because I'm out of time, but in other words, right, there's this natural, if we define, we have this natural splitting of omega 1 c of u prime into the 1, 0 forms. And the 0, 1 forms, right, but these are just a span of dz, and these are just the span of dz bar. But the point is, if phi is holomorphic, the splitting is preserved. And so in other words, the splitting makes sense on a Riemann surface. But it doesn't make sense, of course, if you just have an abstract surface. Even though the splitting makes sense locally in coordinates, it's not invariant under smooth change of coordinates. And in fact, you can see that sort of the splitting being preserved is exactly equivalent to phi being holomorphic. Okay, so I'm out of time, but so next time I'll finish up with this. So I'll see, we'll see how this D operator splits into operators and forms, and then we'll use that to talk a little bit about the de Rham cohomology groups of Riemann surfaces. Okay, so I'll stop here.